All right, the next video here is about gas laws. Gas laws are a way of calculating what's going to happen when you modify something with a gas. So really what we're talking about are equations. We're going to talk about several of them, but first we need to talk about what you can do with gases. You can measure a pressure of gas, you can measure the gas's temperature, you can measure the gas's volume, and you can measure the number of gas particles that are there. So that's P, V, T, and N. Lowercase n is moles, and so moles is just a way to count things. All right, so I want to make sure that we understand that some of these laws are going to be like, oh, that's duh. Like, why did you didn't have to tell me that, I knew that. But I want you to understand that when these laws were first understood, that we were talking about people who couldn't keep their water clean, didn't know what atoms were. We're talking about the 1600s. So it was a big deal for them, but you know a lot more than they do. So let's talk about the first one. So the first one is called Boyle's Law. And Boyle's Law defines a relationship between pressure and volume. So remember I said that it's, whoa, do not want that one. Remember I said we're going to talk about pressure, volume, temperature, and moles. So these first several laws, what they're going to do is they're going to identify two. I'm going to study this, and we're not going to talk about temperature, and we're not going to talk about moles. Okay, so in Boyle's experiment, he did not allow the amount of gas in the container to change. So that's why the mole number is crossed off. And he did not change the temperature of the gas. So that's why we can take that out of the equation. So what he's going to do is he's going to change volume and see what happens to pressure, or he's going to change pressure and he's going to see what happens to volume. Just isolating those two variables. The other variables are constant, so they're out of the equation. Here is his equation. I don't care that you memorize this. I care that you know how to use it. So what Boyle's Law discusses is I have, let's say, a container. So we have this container, and this container is airtight. And let's say there's, I don't know, it doesn't really matter. There's a little bit of nitrogen gas in here. Okay, and the nitrogen gas is reading a particular pressure. And if you push down on this solenoid, then the solenoid's going to be more like that. And the nitrogen has now been compressed. It's in a smaller volume. So what happens to its pressure? What do you think? I took a bunch of stuff and I squished them into a smaller amount of space. The pressure is going to go up. The pressure, remember, is the feeling, the force that is felt when things run into other things. So if I've got these nitrogen molecules in here, they're pounding into the wall, but now they have less space, so they're going to be pounding into the wall more often. And so that means the pressure is going to go up. Another way to think about this is if you were to take, say, a balloon into water and then pull the balloon down, it would be difficult, but pull the balloon down into the water, the balloon would get smaller. Another way to think about this is so I did not agree to go onto a submarine, but I had some friends when I was in the Navy did agree to go onto a submarine, and they said that one of the first things that they did with the new people is they did a dive test, and so they took a rope and they tied it across the engine room and used a winch to make sure that it was incredibly tight. So I had this really, really tight rope, and then they descended, and the submarine went pretty deep, and the rope became slack. All right, so I increase the pressure and then the volume goes down. The submarine literally gets smaller. And then they did the opposite. Once they were at their max depth, they tied the rope really, really tight, and then they ascended up to the surface. And the ship got so much bigger that the rope actually broke. So if I add pressure to a gas, it will get smaller. If I increase the volume of a gas, that means the pressure must have gone down. So the relationship between these two things is inverse. They're inversely related to each other. When one goes up, the other one goes down. All right, so we're going to do a calculation here. I'm going to make it so the math is actually below, and we'll just do it railroad track style. All right, so what I have here is a sample of gas that's in a 2-liter container, and the pressure is 740 millimeters of mercury. I want to know what the new pressure is when the volume is now 1.25 liters. Okay, so what I need is an answer that has a pressure unit. So I'm going to start my railroad track off with 740 millimeters of mercury. So what is going to happen when the pressure goes from, or when the size goes from 2 liters to 1.25 liters? What will that do to the pressure? So I've taken a container and I've squished the container, and it's a smaller container. So what's going to happen to the pressure of the gas inside that container? The pressure is going to go up. So how do I take 2 and 1.25 and turn them into a bigger 740 number? I'm going to take 2 liters and 1.25 liters. So I know I have to put liters in the numerator and liters in the denominator. They have to cancel out. This unit has to go away, because the only unit I'm allowed to have when I'm finished with this calculation is pressure, because I'm looking for a new pressure. Okay, so I put the 2 on the top and the 1.25 on the bottom. That way I would get a number that is bigger than 740, because I know the pressure is going to go up. And so the math on this works out to be 1,184 millimeters of mercury. So if we were doing this with sig figs, we have 3 sig figs. So your answer would be 1180 millimeters of mercury. Okay, that's it for Boyle's law. Again, I don't memorize these equations. I think about what is happening to the gas, and that I make my answer applicable to that. So I knew the container was going to get smaller, so the gas pressure was going to go up. So I got a bigger gas pressure number. All right, so the next one is called Charles' law. So again, we've got P, V, T, and N. And this time we're going to have a relationship between volume and temperature. So we're not going to allow the pressure to change, and we're not going to change the number of gas particles inside the container. Okay. All right. So what would happen if I had a container? So let's say you take a balloon, and the balloon is filled with some gas, and then you take that balloon and you put it into the freezer. Okay. So the particles inside, the gas particles inside the balloon, are going to slow down. So that means they're not going to hit the inside of the balloon as hard. So that means that the volume of the balloon is going to go down. This is definitely something you can do at your house. You can just put a balloon in the freezer and see what happens. The opposite is also true. When I worked as a busboy at a restaurant when I was a kid, the chef used to play jokes on us. And so I decided to play a joke on him. I brought a balloon with me to work, and I stood inside the walk-in freezer for a couple of minutes. And then I took a bunch of huge breaths, and I filled the balloon up as absolutely big as it could possibly be. And then I tied it off. And then I set it next to his desk in his office without him noticing. And I left. And about 15 minutes later, the balloon went off, and I was way far away on my bicycle. So this is definitely a practical joke you can play on somebody. If it's wintertime and there are balloons around, fill the balloon up outside, go inside, set it down next to somebody, and just walk away. So the relationship between volume and temperature is direct. If the temp goes up, the gas moves faster and the volume increases. And if the temp goes down, then it shrinks. So that's our relationship. There is something important that we're going to notice when I do a calculation here. So I feel like this always works out better if we just try. So let's say that I've got a balloon, and the balloon has a 3.5 liter size. Okay. And I want to know what's the new liters when I have the balloon at, let's say, room temperature. So we'll go with 20 degrees Celsius. And then we're going to take that balloon outside, or we're going to put the balloon in the freezer. Doesn't really matter. And we're going to say that it's, I don't know, negative 5.0 degrees Celsius. Okay, so the temp drops, the particles in the balloon slow down, and so then the volume should decrease. So let's write that railroad track. 3.5 liters. I'm going to set that up like that because I'm going to get a liter number out of this. And then I'm going to go ahead and I'm going to write. So I know that the size has to go down. It's got to get smaller. So I'm going to put the little number, -5 degrees Celsius in the numerator and 20 degrees Celsius in the denominator. All righty. So if I do this math, I get 3.5 times 5 divided by 20 equals -0.875. I hope you're looking at that and then asking yourself that what's that? What is that supposed to be? So this isn't a thing, right? Something either takes up space or it doesn't take up space, but it can't take up negative space. This isn't like an Escher drawing. This is reality. So what's the problem with my calculation? My problem is I have a negative sign. Well, the temperature can go negative. True, it can go negative in Fahrenheit and Celsius, but it can't go negative in Kelvin. So all of your calculations with gas laws, if there is a temperature involved, you must first immediately convert that into Kelvin. Otherwise, it just doesn't work. So I will subtract off 273. I don't know why I said subtract. Add 273, add 273, and we get, let's see, with this one, it would be 268K, and this one over here would be 293K. All right, so let's do this again. Erase this, erase this, erase this, and we'll put, I know that it's got to get smaller, so I'll put 268 in the numerator and 293 in the denominator. I can go ahead and cancel out my Kelvin units, and it's going to be a big change. So 3.5 times 268 divided by 293. And I get 3.2. I have 2 sig figs, so 3.2 is my answer. And that's a really big difference from 3.2 to 0.875, even if we're disregarding the negative. The size of the Kelvin numbers, so they're much bigger. So small changes in Kelvin number sizes isn't as influential as changes in Celsius numbers. So we definitely need to use the Kelvin for the no negative and for the correct change in ratio, in this case of volume. Okay. So something to think about with this is these first two laws depended upon the ability of the substance, the container, to be able to change its size. That wasn't an easy thing to do. Plastics didn't exist. Latex didn't exist. So they had to come up with things. So it could have been like a bellows that they would use to heat up like a blacksmith's forge, something like that, or a pig's stomach or a sheep's stomach that they could tie off and have act as like a balloon. Okay. Let's see. There's a calculation here. That's the equation. Again, I didn't even show you the equation before we did the math because I don't think about the equations. I think about what's going to happen. All righty. So the next one is called Gay-Lussac. And so again, we've got pressure, volume, temperature, and moles. And in this case, we're going to not deal with the volume and not deal with the number of moles. So again, we're not adding or subtracting any gas to this. And then the volume thing, so this is a change. This container must be rigid. The volume can't change. So I don't know, steel container, some sort of metal container, glass even, doesn't really matter. It just has to not be able to change. Okay, so think about a can that you have. What would happen if you increase the temperature of that can of gas? So I don't know, like a hairspray or a propane tank or something like that. The temp goes up, the particles inside the container move faster. They start hitting the inside of the walls of the container harder. So the pressure is going to go up. You might have seen videos of people throwing aerosol cans into wood stoves. I've shown that in class before. You can Google aerosol can, wood stove, and these guys from what it sounds like are Eastern Europe go ahead and throw a aerosol can into a wood stove and close it and destroy the wood stove and potentially catch the building on fire. not funny, but also kind of funny because I don't think anything actually happened to them. Okay, so what's important with this calculation? The first thing we have to realize has to be in Kelvin. It's a temperature value, so it has to be in Kelvin. So we'll just I'll just make something up here. Again, I didn't even show you the equation. I don't really care about the equation. So this relationship is a direct relationship, just like the last one. The first one was inverse. Boyle's law was inverse. Pressure goes up, volume goes down. But for these next two, we're talking about a direct relationship. So if I've got, I don't know, let's say the pressure is 1.1 atmospheres. Okay. And I want to know what the new pressure is. I'm going to start off with a temperature of, let's say, room temperature, 22 degrees Celsius, and the temperature is going to increase to a temperature of, let's say, like a really hot day. So like, let's say 45 degrees Celsius. All right. So again, we have to go ahead and add 273 to this, 273 to this, 318K. And then this one here is going to be 295K. Alrighty. So then let's do the math on this. I'm going to start with 1.1 atmospheres because I need an atmosphere number because I'm looking for a pressure. And so we've got an increase in temperature. So that means the pressure is going to go up because those particles will be moving faster. So I'll go ahead and put 318 in the numerator, and I'll put 295 in the denominator. And then I'll cancel out those kelvins. And then let's see what this math is. So 1.1 times 18 divided by 295. And so the temp goes up to, how many sig figs we have? 2. Goes up to 1.2 atmospheres. Okay, that might not seem like a lot, but it is. It's almost a 10% increase in the pressure. So that would be significant. All right, and then the last of the normal, or the first 4 gas laws is going to be Avogadro's law. So remember, we have pressure, volume, temperature, and moles. And this time we are going to talk about moles and volume. We are not talking about pressure, and we are not talking about temperature. So I have a container whose size changes. I'm going to keep the pressure the same and the temperature the same. This is what happens when you blow a balloon up. You take a balloon, you fill it up with air, the balloon size changes. Why? Because you have increased the number of moles of gas in the container, so then the volume increases. So again, this is another one of those direct relationships. One goes up, so does the other one. So this name should ring a bell, Avogadro. This is Avogadro's number. He did not come up with the number. He was the person whose work, this work right here, allowed the people who came up with the number to come up with the number. So he did work, and then this is exactly how science is supposed to work. Somebody does some work, and then somebody else reads that work, and then takes that work to the next step. And so we end up using Avogadro's law to determine what exactly the number is for the mole. So pretty cool. So this time we're going to do volume and moles. So this one could be complicated. It could be super easy. We'll start off with a super easy one. So let's say I've got a container, and the container is 750 milliliters in size. I want to know what its new milliliter size is. If I had 0.35 moles of gas, and then I add gas to it, and I end up, my new number of moles of gas inside the container is 1.25 moles. Okay. So I start off with 750 milliliters because I want a milliliter unit. Volume unit is my answer. I got moles and moles. They're going to cancel out. I'm adding moles to this, so that means the balloon is going to get bigger because there's more stuff inside of it. So I'll put the 1.25 moles in the numerator and the 0.35 mole number in the denominator. I'll cancel the mole values out, and then we'll do the calculation on this, which is 750 times 1.25 0.25 divided by 0.35. And I got 2679. Let's see, we've got two significant figures, so this works out to be 2,700 milliliters. So it got significantly bigger, but that's normal or understandable because we increased the number of moles by a lot. Okay, so this could be more complicated if instead of it saying moles here, it said, I don't know, 0.35 grams of nitrogen. And then over here it says 1.25 grams of nitrogen. The difference is you have to do a mole-to-mole conversion. So you'd say there's, what is it? 14.00 times 2. So you'd say 0.35 grams of N2, and then for every 1 mole of N2, you'd have 28.0134 grams of N2. And so you can cancel out the grams and you get yourself a mole. So if they give you a gram number, you got to convert that into moles first. Okay, that is it for the first of the ideal gas laws. Thanks for watching.